random forests. Bagging plus one more trick gives us random forests, one of the most popular and reliable algorithms in all of machine learning. Last video we learned how bagging reduces variance by training many trees on bootstrap samples, but we hinted at a problem. Today we'll see what that problem is and how one elegant idea fixes it completely. A random forest is bagging plus feature randomness. That's it. You still create bootstrap samples, you still train a decision tree on each one, and you still combine predictions by voting or averaging. The only difference is what happens at each split inside each tree. Instead of considering every feature when deciding how to split a node, the tree only considers a random subset of features. This one change makes an enormous difference. Here's how it works in practice. Say your dataset has m total features. At every single split in every single tree, you randomly select a smaller number m of those features and only consider those m candidates for the split. The typical rule of thumb is, for classification, use m equals the square root of m. For regression, use m equals m divided by 3. So if you have 100 features in a classification problem, each split only looks at 10 randomly chosen features. So why do we need this? Imagine you have one feature that's much stronger than all the others. With regular bagging, every single tree will split on that dominant feature first, and probably second too. The trees end up looking nearly identical, and when models in an ensemble are highly correlated, averaging them doesn't help much. It's like asking the same person the same question 50 times. You don't get 50 independent opinions, you get one opinion repeated 50 times. Let's see this more concretely. Suppose feature A is the strongest predictor. With standard bagging, all 50 trees split on feature A at the root. Sure, the bootstrap samples differ slightly, so the trees aren't perfectly identical, but they're close. When these correlated trees make errors, they tend to make the same errors in the same direction. Averaging correlated predictions does reduce variance, but not by nearly as much as averaging uncorrelated predictions. Feature randomness solves this by decorrelating the trees. When a tree isn't allowed to look at feature A for a given split, it's forced to find other features that are also informative. Maybe feature B works almost as well. Maybe features C and D together capture a similar pattern. Each tree now discovers a different angle on the data. The trees become genuinely diverse, and when diverse models are combined, their errors cancel out far more effectively. So here is the full random forest algorithm. Step 1, create B bootstrap samples. Step 2, for each sample, grow a decision tree, but at each node, randomly select m features and find the best split among only those. Step 3, let the tree grow deep with no pruning. Step 4, combine all B trees by majority vote or averaging. The randomness at two levels, random data and random features, produces a powerful ensemble of diverse yet individually strong trees. To summarize, random forests build on bagging by adding feature randomness at each split. This decorrelates the individual trees, which makes the ensemble much more effective at reducing variance. Random forests are fast to train, hard to overfit, and work well out of the box with minimal tuning. They are the go-to first choice for many practitioners. Next up, we'll explore a completely different philosophy of building ensembles. Instead of training models in parallel, what if we train them one after another, each learning from the mistakes of the last? That's boosting.